This little power pack was sent to me to take a look at, and the person who sent it, I've completely forgotten who it was. I've been looking through Gmail, I've been looking through the YouTube messages. I just can't find who actually sent this, but they were saying that it's a 12-volt power supply, the type that you can either plug into the USB output, or if you plug into the 12-volt output, you can then power 12-volt loads. Quite handy. And it comes with this charger that plugs into the same socket, and you have to make sure it's turned on when you're charging. And the charger itself, which the little green light lights in it when it's even when it's not plugged in, says output 12.6 volts, 500 milliamps. So it's one of these things that you tend to expect it would be charging a bank of cells with the protection circuit and all that built onto them. But he said he'd had it open, and he couldn't see any protection or balancing circuitry. It just looked like a stack of cells. So I think we should open this and investigate it. We'll also open this power supply afterwards. I can kind of guess what's inside that. So let's get the screwdriver in. Oh, bad start. This is going to be one of these really narrow screwdrivers. Look at it. One moment, please. Emergency set of screwdrivers. This'll do. So let's get this open and take a look inside it. Oh, it's kind of stuck together. Is it clipped as well? Have I got all the screws out here? Not necessarily. Oh, it's stuck. Oh, right, okay. Oh, I see what he means. There's just a red and black wire going straight to the battery pack. There's no... Usually with these battery packs... Where's the notepad? There's the notepad. Usually with these battery packs, you have the batteries connected in series, but then you've got a control circuit, and when the positive and negative is applied to that, it goes into the control circuit board first, comes out, and then goes through all the batteries, but there's also a link to the centre of tap of each pair of batteries. And what that means is that when it's charging them, it can charge them independently. When one reaches the full voltage that is required, the 4.2 volts, it can then bypass that but still provide current to the others. So I wonder what they're doing here. Let's investigate. I do actually see... I'll also test this for capacity afterwards. I do actually see little protection circuit boards, but no... I wonder if they've got something else on them that somehow bypasses the current, though you wouldn't think it could do that. Gonna have to be careful here because this is fully charged up. Oh, right, okay, that's quite interesting. I've got my explosion containment pie dish on hand here just in case things go horribly wrong. So let's take a look at the chips in that. The chip is the DW01, and the two other larger modules are 8205 MOSFETs. So that looks just like a standard. It doesn't look like anything particularly special, is this? Oh, this just clicks out. Okay. So it doesn't look like there's any bypass circuitry in that. The only way to find that out is to perhaps stick a meter in series. So I'm going to do that right now. So in just one moment, I'm just going to get a solder iron, desolder that, and stick a meter in series. So I decided to hook this up to the bench power supply because the charger that came with it was kind of regulating the current because it had reached its 12.6 volts. The voltage isn't equal on all the cells. I can show you what the voltage is now, but it's actually pushing up beyond the 4.2 mark. It's pushing close to 4.25. It's not reached that already on some of the cells. So this cell measures 4.23 volts. This one in the middle, which seems to be the highest, if I can get a connection onto it here, is at 4.25. It should be cutting off fairly soon. And this cell is 4.2. So there is a slight imbalance between the cells. I'm going to see what happens when it cuts off and let it settle back. If it cuts off, I'm wondering if they've bypassed the overcharge protection. I hope not. Maybe they're relying on the 12.6 and just approximate equal voltages. Maybe they're only using this for the cutoff at the lower end of the range. I'm not going to let this go up too high. I'm going to keep it on test for a while, but then I'll come back in a moment and tell you what's happening. So the charge current has now just cut off. Let's check the voltages across the cells. I'm guessing the middle one cut off first, so let's do the top one first here. 4.2 volts, okay. The middle one, which is the one that was going highest fast, is, trying to get a connection here, 4.24. It peaked out about 4.2, just nudging on to 4.26, which I think is tolerance of the DW1. And this one is 4.22. So really, I'm guessing the middle one is the one that's broken the circuit here, and it really is fundamentally, whichever reaches its charge first is the one that's going to break the circuit. So let's disconnect this now. And that means that if the cells do become imbalanced in any way, then the charging isn't going to be even in all the cells. Let me just grab the notepad. Again, let's put this little lithium bomb out the way here. Make sure I don't short it around like that. So what we've got here is these cells are actually configured like this. We've got the 3 cells in series. We've got plus, but it's just going straight in, then there's a protection circuit, then it's going out to the next one, it's got a protection circuit, out to the next one, protection circuit, and out to the next to the negative. And all that's happening here is if the cell capacities were absolutely 100% identical and they all started off the same state of charge, then one of these is going to reach its 4.2 volts out of 4.25 volt limit, and it's going to break the circuit. So in this case it was the middle one, it kind of broke the circuit and stopped the others charging. But if this one had only been up to say 3.8 volts for any reason, if it had somehow imbalanced the others, then that one would only be charged up to say 80% or just under 80% of capacity, but the current would still cut off because this one did reach its 4.25 peak that the DW01 cuts off. And this also means that because that one's got a lower capacity, lower charge put into it, when you discharge them, this one's going to reach it. Say this one went to about 4.2 volt. This one, with the lower capacity of about, say, 80% charge, is going to reach its discharge level first, which is round, I think it's about 2.5, the DW1. And when that happens, when you discharge it, it's going to cut off. So each time you charge it, it's going to be this one that terminates the charge and this one that terminates the discharge. So that means that just because they're not balanced, if there was any sort of variation crept in, I don't know what likelihood there is of that, if that's going to creep in. Don't know. Another thing, I did try plugging a 5 volt load into this earlier on and it didn't work. Not sure what's happened here, but the little boost circuit here has a little crater in it, so it's dead actually. Not sure what happened there unless it's been shorted out. So that's strange. I've never seen this approach taken before. I've always seen the balanced one that, basically speaking, when that gets up to about 4.2, it will still allow current to flow down and through the others, and then when that one gets up to 4.2 or whichever sequence, it will always allow current to flow through the other ones until they all come up to their voltage. But this one does seem, I don't know how that's going to change over time. But anyway, that is a very interesting thing to see. I kind of want to try charge and discharge it a few times. That would take ages. To actually get an effect of seeing how they varied over time, or if something happened that made a cell vary in capacity. Very odd. Let's open this now and see what the quality of this is like inside. I can pretty much guess what's in here. It's going to be super simple, with super simple voltage threshold detection. It's these horrible ones. I don't think there's a screw under there, is there? Nope. Let's pop this off and whip this circuit board out. Okay, it does have, it smells electronic. We've got a transistor here. There's a little surface mount transistor. Okay, mains come in. goes to a bridge rectifier. There's also a 0 ohm link which is being used. They seem to use these 0 ohm links either as fuses or current limiters and fuse. In this case it looks like a 0 ohm link. Goes to the bridge rectifier, then the smoothing capacitor. The circuitry here is very much classic 2-transistor arrangement with a little surface mount control transistor in the bottom here, unless that's a little switch mode control chip. Very hard to see these days. Some of it's just a transistor and some of it is marked. It's marked, it's got flux all over it. Let's see if I can get the flux off it. No, I can't. It looks like a standard transistor. J3 something, J3 smudge. I think that's a standard transistor. Equally, I think this will be another fairly standard transistor on top. Can't really read the number on that just because it's tucked right in, so you can't get the magnifying glass in. This is almost certainly this little transistorish device here. It's a TL431, so it's got the voltage reference here. It's been set by resistors, and when it turns on this opto-isolator, which shuts off that side. And the other thing that will be here, a little transistor tucked under here, so it'll be a very simple circuit that it'll be that situation that the green charged LED is on all the time, but until when the voltage reaches a certain threshold, it turns the other LED off, and so it will be red to show it's charging, but that will swamp the green. And then when it's come up to the voltage threshold set in the simple circuitry, that will then light the red LED and swamp the green out. So should I say, the red LED will go out and you'll be able to see the green. It's a very common technique for doing that. So a very typical little charger. I wonder what the voltage of this output is. There's one way to find out, and that's to stuff it into the mains. Yeah, I should have thought that before. Right, okay, let's be precarious here. Try not to blow it up. And let's stick the leads into the end. So negative to the shell. 12.65, it's pretty close, isn't it, for the desired voltage? Okay. So yes, it's an interesting approach. Now I just have to wheedle this out without touching anything. There we go. It's an interesting approach. I've never seen that before. I'm going to test this for capacity now and see what it is. They quote all sorts of capacities in this. For instance, they say output DC 12.6 volt, 4,800 milliamp hour. But they also say output 5 volt at 10,000 milliamp hour. And I think this was sold as a 10,000 milliamp hour pack. But in reality, they're kind of cheating the figures there just to make it look bigger. And I'm wondering if they've done that thing where the cells are, say for instance, what was it, 4,800, what's 4,800 divided by 3? Where's a calculator? Are they actually 4,800 cells, or is it 4,800 divided by 3, or is it roughly 1,600 milliamp hour cells that they've just added them up like they do? You don't do that for when you've got them in series like this. If that was a single cell, it would be a 1,600 milliamp hour cell, and if you stick 3 of them in series to create the higher voltage, it's 12 volts at still 1,600 milliamp hour, because that's the current you're going to get over time at the higher voltage. I'm not sure if what they've done there, if they've done that or not, but there's one way to find out. I shall put that in the description below, because it's going to take quite a while to discharge this fully and then charge it again under test. But that was very interesting to take to bits. As I say, it's something I've not really seen before, not using a balancing circuit. So it'd be quite interesting getting your feedback on what you think about that, where you think the cells are going to drift over time. So very interesting.